Tonight is February the 4th, 2020. I've got an amplifier here for you tonight with a discussion of a number of things about it I think you'll enjoy. I hope you do. You've seen this amplifier in a slightly different form. Posted a video on it a couple of months back where I had what's called a Poseidon board right here. It had a 12AX7 and a 12AU7, and it had two 1625s over here. And I don't know what I got out of it. I don't remember. It's posted and it got a lot of views and some comments, so I think you guys enjoyed it quite a bit. But it just didn't satisfy me, so I took out that Poseidon board, put in an aluminum plate, and this is a Williamson circuit right here, driving a pair of KT88s. Now this one rocks. This one will do over 80 watts. I'll show you. I did change the rectifier out right here. I had to put a solid state rectifier in it because they're a single 5U4 or a 5AR4. They're just not rated high enough current to run an 80 watt amplifier. I mentioned several things about that in a video earlier, that a single 5U4 is, if you really want to be conservative about it, is probably not good for an amplifier over about 30 watts output, because the overall efficiency of the amplifier, to be conservative again, is probably about 50%. So that means that for 30 watts output, you're wasting about 30 watts in heat. So your 5, your 4, your rectifier, whatever you're using, 5AR4, etc., is going to be having to deliver about 60 watts to the circuit. Now we know that a 5AR4, for example, or even a 5V4 will have a whole lot less voltage drop than solid state rectifiers. But unless you're just, you know, and I completely understand, unless you're just completely enamored by vacuum tube rectifiers or even mercury vapor rectifiers, which I seem to be, solid state rectifiers really are the smart way to go. The mercury vapor rectifiers are pretty exceptional. You know, the voltage drop across them is usually constant at something like around 10 volts. So if you really want to deal with them, they can be pretty impressive. They can do some very very impressive work. You know, of course, with the addition of the heat, the filaments, supply, etc. But anyway, let's get to the point here. This amplifier I am very pleased with. I've been listening to it. I have a bias balance right here, and I have a like I say, a plug-in type 5U4, if you want to call it that, substitute. It's actually, I can unplug it with power on. That doesn't hurt anything. It's actually called a 1N1239, if you can see that, in case you want to buy one. 1N1239. If you look for that, like on eBay, this is what you'll find. It's rated at 3200 PIV, etc. Anyway, okay, let's move over to some schematics, and I want to show you where I'm going tonight with this. A number of you all have asked me for schematics. I don't do a good job of drawing schematics like I used to, but this is a really good one to start with. This little heat kit, this one is for the Williamson type amplifier, W4AM. You can find all this on the internet. No, not necessary for me to put links in there. It's just too easy to find. This is an excellent place to start, in my opinion. You know, you don't have to build this exact amplifier component for component. But what I do is I like this setup right here. I don't go to all this trouble right here. That's not quite necessary. You do need a resistor right here in series with a grid, even if you put that into the wiper of a pot so that you have a gain control at the front end. You do need a grid stopper right there. Not because, yeah, well, because of stability. That's exactly why you need it there. Because when you get the gain pot down at a very, very low value, maybe just a few ohms, it can actually throw this tube into oscillation. Okay, but if you look at the values from here back, from here back on just about every Williamson amplifier, you'll see they're all about the same. 22K here, 47K here, 47K there. Now there's some things in here that I usually don't use. I usually don't use this little stabilizing circuit right here, 4.7K and a 420 picofarad or something in that range. That's to stabilize the amplifier. It just knocks the heck out of the high frequency response. So if you don't have instability issues, then I think it's better to leave it off. Same thing out here. See, they use a Zobel network out here, the 0.1 and a 47 ohm resistor across the transformer. I don't use those either unless I have stability problems, and if I have stability problems I try to figure out a better solution. That again will knock the heck out of the high frequency response. If you don't use their exact transformer, you will have to tinker here with the feedback resistor. You may or may not even want to use this capacitor. You got to be very careful with that capacitor. I've experimented a lot with that. You want to get your voltages pretty much what they have in here, you know, with voltage dividers here with decoupling capacitors. By the way, I don't think I've ever mentioned this before, but I'm not sure everybody knows what a decoupling capacitor is. For example, let's look at this. This is the plate load resistor for this tube. We know that, don't we? And it comes down here, and here's where it gets its DC. And it goes through a voltage divider right here between this resistor and this resistor so that the voltage is correct. But this capacitor off the ground, why is that necessary? Well, in case this is not fully understood, there's two components we have to deal with in an amplifier. One is the DC voltage and the other is the signal voltage. Now if you didn't have this capacitor here, this resistor would be in series with this resistor. It'd also be in series with this one, and weird things could start happening. But you wouldn't have a 22K ohm load resistor for the signal. You would have a 22K ohm resistor and a 22K ohm resistor, and you'd get the correct DC voltage here. But once you start putting a signal in and driving it, and the AC component is on it, then this resistor would be in series with it. But when you put this capacitor here, it grounds this point right here for the signal voltage. So the signal is developed across this resistor basically to ground at this point, because a 20 microfarad capacitor off to ground is going to take all the signal component to ground, so the DC signal stays constant and the load resistor is only this one right here. I hope that makes sense. It's actually pretty obvious that you have to deal with the AC component and the DC component. But anyway, I generally build this circuit right here backwards. I don't always, but this is actually quite a nice setup. This is a balance. This is to balance the cathode currents. You can also put one in right there like UTC does to actually set the cathode current to what you want. You could make that one variable. So this one sets it, and this one right here makes them equal. And they've got their little jacks there to measure it. See, this is the same thing. When you put this capacitor right here, I think all of you know that when you put a capacitor like from here to ground, you get a lot more gain out of it. And that's because the AC signal is grounded at that point. The output power will drop significantly if you leave this capacitor off, because now the AC component coming in on the grids and being on the cathodes is having to work itself back through this resistor network to ground. Okay, enough of that. Okay, so when you build an amplifier like this, you don't have to build every component in it exactly how the schematic is. You notice they use 1.5V4. It's a pretty low powered little amplifier. The only reason they put these capacitors in series right here is just to raise the voltage. Okay, so this amplifier that we're looking at right now is basically built like this right here. I'm using a fixed bias supply, and it comes into a 10K pot. These 100Ks and these 47Ks allows me to adjust the bias on it and balance it. See, this one's going to go up and down, so I'm balancing it. Now in mine, and the one I just showed you, and we're going to focus on it entirely tonight, I've also got a bias adjustment. Well, this one does too. See, it has a bias adjustment right there, so you could set the bias, and here's where you can balance the bias and the cathode currents. I'll show you how to do that. Look at that, what they use. They use two 5V4s. The plates are in parallel for a pair of 6550s. That will work. But if you're going to use anything over about 30 or 40 watts, you're going to have two 5U4s or two 5V4s or two 5AR4s, unless you want to go solid state. So there you go. See, here's how they do it here. They do the same bias balancing over here, and in this case, well, they're using 6550s too. They rate this amplifier at 50 watts. Okay, now the let's see, the exact one. Here's a beautiful design right here, just component for component. This is the UTC W20, as you can see. This is another Williamson circuit, just drawn a little bit different. But if you follow it out, you'll see it's exactly the same thing. And see, and there's that resistor for setting the cathode current, and there's a resistor right there for balancing it. Here's another thing. If you're going to use parallel push-pull tubes, like a quad right here, like they use a quad of 6L6s, you really don't want to strap the plate to the plate directly with a piece of wire. You don't want to strap the screen to the screen with a piece of wire. I don't know exactly why, but you need to give the screens of the tubes and the plates of the tubes, I guess for lack of any other way that I can explain it, you just got to give them a little wiggle room there. And all they do is put 47 ohm resistors here and 100 ohm resistors there. And I found that absolutely stabilized that quad 1625 modulator that I built. Made it solid as a rock. Up until then, it was squirrely. So be very careful in a quad how you connect the plates and the screens together. That's my advice. Don't do it directly. Let's see. I believe that's all of the schematics we need to look at right now. This is one I believe that uses, oh goodness, well that's okay. Let's go back to the amplifier. Before we get totally into the amplifier again, I guess if you go out and you look for 100 amplifiers part 1, 1916 to 1945, part 1. Part 2, 1945 to 54. Part 3, 55 to 59. And part 4, 59 to 82. I find these schematics so valuable that I did exactly this. I printed every one of them, even in color. They are so important to me. I don't know if I can show you color photos in here or not, but there's some really nice ones. I think some of these oldest ones have some really nice color photos. That's not what this is. Well, you see there? Well, you gotta have these. They're free. I mean, it'll cost you the ink or the toner and the paper and the binders, but and you don't have to have them in hard copy. Of course, you can have them in file format, but these things are good. This Lilienthal Engineering. Yeah, I'm going to put these back. I just brought them out here to show them to you and how to find them. You just look at 100 amplifier part 1, 2, 3, 4, and you'll find them all. So that is such a valuable resource. I didn't want to forget to tell you about it. Okay, let's look at how the amplifier is set up. I am using, first of all, these are they're stamped Telefunken KT88s, but all of you that are familiar with vacuum tube know that these are actually JJs. But I have found that they're actually quite expensive too, these Telefunkens. But today, just like it was, 75 years ago, all tubes are not made the same. They may be made the same, but they don't perform the same. And I can say here that I've had these for a couple of years. They perform extremely well. They must be the very top of the line that JJ makes. And Telefunken buys them and puts their label on them. GE and RCA and Sylvania and Mullard and the whole 9 yards of them did this 60 years ago, They did it too. They made, I guess, RCA said we're going to make 1,000,000 12AX7s, and Mullard said, well, we'll make 1,000,000 12AU7s. I don't know. And they sold them to each other and put each other's name on them, and then they graded them too. So anyway, I'm not trying to sell you these tubes. I'm just telling you that they perform extremely well. And not only that, they have, I want to show you the balance. This amplifier, I've been using it now for 2 or 3 months, and I want to show you the balance. I'm actually shocked. Not shocked. No, I don't want to get shocked. No electrocution. 0. But I want to show you the balance between these two. I use a 1 ohm resistor in the cathode circuit. Let's zoom this guy in right there. Oftentimes you can see it better in the camera. I can't see that 0.067. That's 67 milliamps across a 1 ohm resistor. I'm going to move it to the other side. And the other side is 67.0. That's even kind of shocking, again, no pun intended, to me. 67.0, you know, they fluctuate slightly. 65, back to where I started from. Wow. No, I promise you, I'm moving it left to right. So the balance is just, I'm moving it from here to here and back and forth. So anyway, that's the balance pot, and the one in the back, the bias set, sets the overall level. So they're perfect. You want them set about 70 or so milliamps. I run the bias on my tubes actually quite hot. I run them up at 80 or 90% of the maximum plate dissipation. They run quite hot. I'll show you how hot they are. Get my meter over here. I'm trying not to forget anything, because there's some little things that I've learned and really enjoy. See this tube? Can you read that? It's about 370 degrees, 360, 70. Let's pull this off. Let's measure both of them. And since the current is just essentially exactly the same, see, this one is 360, 70. About the same. I hope you can read those numbers. It's reading about 300, and it fluctuates between 300, well, it's setting them about 360, to somewhere between 60 and 80. And same over there. Very, very good. I am extremely impressed with these tubes, and I have another set of them too. Anyway, that's what that is. Now let's set this guy up on its side and take a look underneath, and I'll show you what my thoughts on that. Okay, well, some of the things I want to point out in this amplifier that I think are important, that I like to use, and I'm using a non-conducting rod here. I know some of you have reminded me that I have to be careful with that, especially using a pencil, because it is still on. This is the way I put my capacitors in there. These are like 100 microfarad, I think, which is actually quite large. You don't need to make these things monstrous, 500 and 600 or 1,000 microfarads. It just isn't necessary. But I put them in with just a little bit of goop on the bottom. Goop is a material that I've shown, I believe, before, and it's a miracle stuff for me. That's what it looks like. You can put a little bit on there and it'll hold just fantastic, but you can pull it off. Anyway, in series and parallel, whatever you want to do. Same thing over here. This is the high voltage supply. This is some decoupling, and I'm not sure what all. Yeah, this is the bias over here. Here's the bias supply. Decoupling capacitors, high voltage capacitors. I had a much smaller choke in here. This is a 500 milliamp 1.5 Henry. That changed things dramatically. Now, as far as like the component values, as I said, if you're going to build this circuit, you want to use these types of voltage dividers, but the one that you're going to have to tinker with the most, or the only one you're really going to have to tinker with, is that one right there, because your supply voltage may be slightly different right here. If you want 450 and you end up with 500, that's actually okay, but you might want to play with this one. You might see, this is 1.5K at 1 watt. I put one in here. This one ends up being if I could see it, 5K for whatever reason. That gave me that gave me the correct voltages on this part of the circuit, and that is fairly important. As far as the bias supply, here's the bias control right here. There's the balance. See, there's those 100K pots and 100K resistors and 47K ohm resistors. I use orange drops. I love them. Here's feedback right here. I am using a capacitor in this one. You can put in some suggested value, unless you've got some, unless you've got the equipment to really deal with it. You may be better off just leaving that capacitor out. Either that or putting it in pretty darn small, 100 picofarads or so. They suggested some stabilizing stuff off the screens of the tubes. See, there's where we measure them. I think that's it. See, I just put a piece of aluminum in there to mount those tubes on. I do not the 6SN7s. This is the Williamson driver feeding a different amplifier design bias circuit so that I can feed a negative voltage to the KT88s. I use a small capacitor right here on the output of the bias supply that actually feeds the grids. At one time I put a big one in there because I wanted to make sure my bias voltage was very, very, very clean. And when I say a big one, I'm talking about 100 microfarads. But I found out that as monitoring it, it takes it like forever to build up because you got some series resistors in there. And I just didn't think that was a good idea. So I think this one's like 1 microfarad. Doesn't take much. That's pretty much it underneath. Not too exciting, I don't suppose. Let's run some power tests on it. I do want to show you something here before we get too far away, because this might be a reasonable question to ask. What do I set the plate dissipation for? Well, here's our plate voltage. Let me see. Let me zoom in on it. Sorry I have to do all this, but 577 volts. And if you remember, 577, and we were running at 67 milliamps. That's 0.067. That's 38.6 watts. The absolute maximum power rating, maximum absolute plate dissipation is 42 watts. And if I divide that by 42, I'm running it at 92%. You can see that 0.092. So I do run them hot. That's just my choice. I'm not saying that's how you should do it. You probably, for sure, will get better performance running them really hot. Will it shorten the life of the tube? Oh, I suppose so, but I'm not too worried about it. I'd rather have performance out of it and replace the tubes there once in a while than have lower performance and have them last forever, although quite honestly I don't think we're going to hear the difference. But anyway, that is what it is. So and 577 volts is not terribly high for KT88 6550. Thought I'd throw that in there before I forgot it. Okay, just to start the test here, we'll start it out at the rating of the transformer, 65 watts. There's the 65 watts right there. That's its average power, 0.7% THD. Here's its voltage across 8 ohms. You can square that divided by 8 and you'll get this number down here. There it's a kilohertz, so there's what it looks like. That's a 65 watts at 1 kilohertz, so it does actually quite well. Absolute maximum power, that I call my absolute maximum power, at 1% THD. We'll watch this guy right up here till we get it up to about 1%. And we'll also see some nice symmetrical clipping in there too. There's one point, there it is. There's, I'm not trying to split hair, but there you go. That's pretty much 81 watts. So it does a good 80 watts. I don't see any clipping in there. I can see the tiniest amount of where it's starting to clip. If I turn it up a little bit more, so you can see the clipping there. The clipping is nice and symmetrical at 87 watts, but it's up to 4%. So it should be quite a rock and roll guy here. Okay, so it'll do 80 watts before any clipping occurs. So it seems to be performing quite well. To me, that speaks extremely well for the Williamson driver. So, you know, just make sure that you don't have rectifiers where the voltage sags terribly, because it's going to work great at 30, 40, maybe even 50 watts, probably not. 40 watts below, it's probably going to perform pretty well, but once you start getting above about 40 watts, it's going to start performing pretty bad, and you're going to go, well, what's the problem? Well, your voltage is sagging pretty bad. It's going to drop. It's going to drop because of, well, I've got the line voltage stabilized at 120 volts input, so our line voltage coming in is not dropping. But just because of the internal resistance of the transformer, it's going to start dropping some. Even though that's a pretty hefty transformer over there, it doesn't matter how big it is, going to drop some. So you see what I mean. Solid state rectifiers will give you a lot better performance. Let's do some frequency scans of it, and then we'll let it go. Okay, now we're going to do some scans on it. I'm going to show this for any newcomers I might have that's never seen this equipment. This is an HP8903 audio analyzer, and it'll do scans. It has an HPIB interface on the back with another interface connector on it that interfaces it to a USB port on a computer. It's all controlled by the computer, and it's down here, this little PC. And what we're going to do is run THD scan on it. So we'll start that up. And it asks us right here, we start setting the parameter. I'm going to set it, we're going to start at 30 hertz. We'll go to 20 kilohertz. We'll go to 20 kilohertz. 30 to 20 kilohertz, 5 points per decade. That gives us a decent, smooth, let's see, get some of that glare out of there. There you go. And then we're going to set the generator level to 2 volts. Now, even though it's set to 2 volts, we're not going to be pumping 2 volts into it, because we're let me turn out another light here. Get all the glare off we can. And then what I'm going to do, even though I've got the generator level set to 2 volts, again 30 hertz to 20 kilohertz, 5 points per decade, and then we say down here we say start. And then it says, okay, it says reference level okay. It wants to know what our output voltage is. We're going to have to look back over here. And what I've done is I've adjusted the level right here, the level of the input. As you can see, this cable going up here, the output of the 8903, and I've got it set for 50 watts. It's dropped ever so slightly. Let's make sure we're at full 50. And the reference level is kilohertz. So we say, yep, everything's fine. And we can monitor it right here. I want you to see it. There's our kilohertz. And then we say, okay. Now watch what it's going to start doing. It's going to start out at 30 hertz. There's our line right there. Starting out at 30 hertz, it's about 0.85% THD. So this is the 1% line right here. So it's staying well below. It's staying below 1%. We're running at 50 watts. Remember, that's basically what the designs are set for, is about 50 watts. At least that's the one that I have built it by, with that in consideration. I'm also very conservative about amplifiers. If I say it'll do 50, I expect it to do at least about 70. Now it goes up a bit here at the end. I'm trying to stop it at 15 kilohertz, but these numbers don't exactly, this stop frequency doesn't exactly stop it at that. So we just got to deal with what we can get. We can change it around. But anyway, it's below 1% until we get out to about 8 kilohertz, and then it starts to 1%, and it starts going up. So 15 kilohertz would be, there's 10, there's 18, so 15 kilohertz would be around there. It'd be around about 2.5% THD at the high end. Now you're going to say, well, what about that transformer? That transformer right there, it says right there, 7 hertz to 50 kilohertz. Can you see that? Power level 65 watts. Well, good luck. It doesn't work that way. And there's no other design that's going to make it work that way either. Now, is this going to sound bad? Not at all. I think it sounds marvelous. But that is the way it performs, and that's the way it is. At 50 watts. Sounds great. Got a lot of power to it. I mean, it really, I listened to it out here in these little paradigms. They're called Focus. It's a little bit dark in here. If you can see it, I got one on the right side. And I've just got them parallel, and one on the left side over here. And it'll rock and roll in here. So that is a Williamson design into a pair of KT88s. Built it about as good as I could do it into quite a nice transformer. The only transformers that I have and that I've seen and that I've built with that actually do 20 to 20 kilohertz below 0.5% is either one, a Macintosh transformer, which does exceptionally well, or the Acrosound transformers, or the UTC transformers. Well, actually the James transformers perform quite well too. I've built amplifiers with all of those. I've posted videos on all of those, and that is my experience. Those are the ones. Other than that, I generally think of an output transformer as a 30 to 15 kilohertz transformer. Now, if you actually look at the real specs on some of the amplifiers that we have a lot of respect for, like the Dynacos, they're actually rated 30 hertz to 15 kilohertz. So there you go. I'm not putting them down. I like them. I think they're actually quite good devices. I want to run one more test for you though. Okay, what we have here is this is the box. This is where the output from these resistors. By the way, this amplifier down here, this wire right here, this cable right here, goes up to these dummy loads. These are precision resistors. Goodness, it's getting windy out there, opening my door. These are precision resistors. Let me see, have I got something on the front of this thing? There we go. 1% non-inductive. Anyway, they do a great job. I can switch between left and right channel, but we're just using it on one channel right now. And it all goes over to this breakout box. And this breakout box is what feeds everything. So what I've got set up right now is basically the same thing. There's our sine wave, there's our output power. I'll drop it down to 50 just so that we can stay about the same. Okay, add a kilohertz or thereabouts. I set the kilohertz up here so I'm not, it doesn't have to be exactly 1000.0. There's its THD right now. Sorry for the glare. There's its THD again. And what we're running over here is a program called Spectra Plus. Now I'm going to hit run. There it is. See it? It's running. You can see everything wiggling. I'm going to turn out some more lights. Hope I don't put it in too much of dark. I think you can see it running. There's our fundamental. 1 kilohertz. There's 2 kilohertz, 3, 4, 5. It's got a lot of harmonics in it. Vacuum tube amplifiers are going to have plenty of harmonics. The second harmonic, this is 10 dB per, 10, 20, 30, 40, about 43 dB down or so. Now it's quit running, but at least we still got the display stable. That's a harmonic profile of that amplifier. Sorry for that glare. It's got a terrible amount of glare on it. But anyway, I can't do the video over again here. It'll just take me too much. I can only apologize for it. Now, one of the things that's really nice about this program is, see the 60 hertz over here? See there's 60 right there? If you've got like a hum balance pot in it, which I do, you could tweak that down, up and down. You can see it real time occurring. I'm going to start it running again. Yeah, so you can see the lines wiggling. It only runs a few seconds and then it pauses. and freezes. But you can adjust the hum balance right here. See the hum, this is about minus 100, and this one up here is about minus 20. So there's about 80 dB difference between here and there. So you could, not quite 80, 76 or 77, you might actually want to, you could estimate that as the signal to noise ratio, because that's about what it is. The fundamental frequency too, it's a 60 hertz component down here. So that's a marvelous little program to have, along with this one over here. I've made a lot of videos on this stuff. This program is made by a good gentleman by the name of Pete Millett. You can go to PeteMillett.com and find all this stuff. It's not easy to configure this audio analyzer up here to work with it, but it's worth the trouble in my opinion. So there we go. We're still running it at 50 watts. I'll tell you what, let's do. Let's just for the heck of it see. Let's run the power up a little bit. Okay, there it's running. By the way, here's THD, see about 0.7, which agrees with our Tektronix and our HP stuff. Let's see what happens if we run it up to about maybe 75 watts. Let's don't go over the edge here. 75 watts. Now let's look at it. You start seeing a lot of spurs in here. Well, our ears hear all that. That doesn't mean that we don't like it. I'm actually convinced that for some reason or another that I can't quite explain, we seem to like a lot of the artifacts of a vacuum tube amplifier. I mean, it's got the full range out there. If you look at a really, really high quality amplifier like, again, a Mac amp, this will be quite a bit lower. It'll actually be lower than the third. This right here, a triangular wave has a descending set of harmonics right here, a harmonic profile. And if you look at a single-ended amplifier, that's exactly what you'll see. Now, it'll look like a sine wave on an oscilloscope, but it's practically a triangular wave. The second harmonic, if this was an SC triode, SET, single-ended triode amplifier, the second harmonic would be up here, the third would be there, fourth, fifth, sixth, seventh. And you can almost draw a straight line right across the tops of them. I don't build SE amplifiers. I'm not saying they're bad, to each their own. But that's it right there. So there you get the harmonic profile. Here you get the frequency sweeps. And these things will do more than that. But that's the equipment that it's always fun to play with. Power meter. You can also make the Hewlett-Packard read power. You can say clear, 19.08 special. Well, no, this thing's got control of it. Clear, 19.08 special, and there's it, and then it reads power. See, it says it's 74.7, 74.7. This is a jewel to have. If you could get one of those in good shape, and you like to do audio work, you'll love it. But see, there's its THD at a kilohertz. It's only 0.78% at 75 watts. I'm actually quite pleased with it. Like I say, I mentioned a while ago how the Acrosound transformers, the James transformers, the UTC transformers perform really well. But pretty much the maximum power is about 20 watts. You could make an amplifier for 20 watts with a Williamson design. I think it's about as good as has ever existed on Earth. But when you start getting higher than that, things get a little bit more complicated. So there you go, ladies and gentlemen. I hope you enjoy this. This is the first audio video I've made in audio equipment video I've made in quite a while. I want to show you something very quick. This is one of my next projects. I got to turn some lights back on. This is a push-pull amplifier with plug-in coils from 1948 that I hope to have on AM here pretty soon. I've been spending a lot of time. It is so darn dark in here. I'm not quite sure why. But there you go. This one was made by James Millen down here, as you can see. It's got a plate current meter and a grid current meter. It uses a pair of not 8/11s, but I can't remember what they're called. Anyway, they look like 8/11s, but they're a lower gain tube. Uses link coupling. This is how you couple the antenna. This is the tuned circuit here, and then you couple the antenna this way. I've also been into my astronomy a lot lately, but that's for another video. Well, thanks for watching. Stay safe.